leveraging ubiquitous computing for empathetic routing. With the increase in automated driving assisting systems, the vehicles and cabin space is gradually transforming to a mobile built environment in which the drivers and passengers spend less time focusing on driving and more time on other activities. The changes in scenery, traffic patterns, noise level, and even road type may significantly impact drivers' state, comfort, and behavior. For instance, research suggests that road features, road type, traffic condition, and drivers' familiarity with the road can positively and negatively impact drivers' emotional state and behaviors. This suggests route options could significantly influence the driver and passengers' emotional states prior to reaching their destination. However, the majority of routing services provide options only based on identifying the fastest route or shortest distance to the final destination. In this research, we propose a framework for humanizing routing services. Through our proposed empathetic routing framework, we categorize different routes and locations in a city based on how they affect drivers' stress levels. The empathetic routing framework consists of 4 sections. In Section A, we collect data using conventional wearable devices, which includes drivers' biomarkers, location, hand movements, and other behavioral or environmental data. We send these timestamp drivers' behavioral and physiological data, as well as the GPS locations, to a computing unit. In the computing unit, we perform pre-processing, such as standardizing heart rate and calculating heart rate variability features, which has been shown to be correlated with the stress levels. We then match heart rate and GPS locations based on timestamp, and we find the associating infrastructural elements to each GPS point using a mapping API. From that, we create a database of different infrastructures that could be associated to high heart rate concentrations. Once a user requests routing, we first assess if we have enough data from that user. If we do, we perform route selection based on users' personal inputs or users' heart rate data from the past. If not, we use the created database, and we basically provide routing based on the aggregated data from all users to avoid high heart rate concentration areas. For instance, we collected data from 21 participants in the city of Charlottesville, and you're looking at the standardized heart rate throughout the city of Charlottesville in different days and months of the year. Based on the GPS locations, we also provide a heat map of heart rate in the city of Charlottesville, where we can see different locations that are associated with higher or lower stress levels. We then use a case study to provide the application of empathetic routing for ranking 3 routes between points A and B in the city of Charlottesville. We have 3 candidate routes, and we compare these 3 routes based on historical heart rate data. Route 1 passes mostly through a highway that has a relatively higher speed limit, more noise, and fewer intersections. On this route, the driver has to drive through 3 busy intersections, 2 ramps, and 2 merging on or off highways. Route 2 passes through a residential neighborhood that has a relatively lower speed limit, a lower noise level, and a higher number of intersections. On Route 2, the driver passes through 1 ramp, 2 busy intersections, and 1 fairly tight road segment, which has a higher traffic density. Route 3 passes through the main streets of the city. It has a relatively average speed limit and medium noise level. On Route 3, the driver passes through lower traffic density areas in 4 intersections. To choose between these 3 routes, we perform a Welch t-test. As you can see, the historical HR data is used for the comparison, and the Welch t-test shows that route number 3 has the least HR standardized value, which means that it is the less stressful for the drivers. Although in this study we have only demonstrated the application of driver's heart rate, multiple other measures, such as driver's hand movements or light and noise in the environment provided by the smart wearable, can also be considered. The outcome of the presented framework can be used by city planners to provide a more holistic overview of the effect of different areas of the city on the drivers, or choosing different design options to potentially decrease drivers' stress level. Additionally, in our study, we have not considered the differences between the hours of the day, different genders, and driving experiences while choosing routes. Contact us if you are interested in our research. uvabrainlab.com